Okay, so today I want to do a lesson on Eulerian graphs. So there's a new term for us here and a theorem, which is perhaps not surprisingly due to Euler. Uh, but I actually want to start by saying just a couple words about the history here. This is just a quick little aside, but it's a nice story, and this is kind of arguably where graph theory came from. So, as you probably know, Euler is one of the great mathematicians. He's sort of, clearly like top three of all time, and he's vaulted our understanding of mathematics forward he just carried us forward a tremendous amount in lots and lots of different directions. This is kind of a small thing that he did in a way, but it's arguably the start of graph theory. So Euler comes from a town called Königsberg, and it was asked in the town of Königsberg. So there's a river that runs through it here, and it was asked, is it possible to take a walk that would permit you to travel across each bridge of Königsberg exactly once? So you can start wherever you want, you can end wherever you want, but you have to take a walk and traverse each bridge exactly once. And no using helicopters or anything like this, right? Of course, they didn't have helicopters, but anyway, so we just want to walk along and traverse each bridge exactly once, and no one could see how to do this, but why was it not possible? And in the end, the reason here is not deep, but what Euler was able to do was crystallize the right setting in which to think about this problem, and that is graph theory, and that's what brought him to introduce the concept of a graph. So now, we're already equipped with the concept of a graph. We know all sorts of things you can do with these. When we look at this problem, it's maybe not so hard, but what Euler did and what we will do now is the following. We'll create a vertex for each landmass. There we are. And then we'll have an edge for each bridge, right? So here you have a bridge connecting these two. Here's another bridge. Here's a bridge. There's a bridge. There. And there. And there. And, okay, now maybe let me just redraw the graph to make it look a little bit nicer. So here's our graph. Well, what does this problem come down to? Well, of course, as you're walking along, you move from one landmass over a bridge to another landmass. Well, that's just starting at a vertex, walking along an edge to another vertex in our graph, right? So this question of, is it possible to take a walk where you traverse each bridge exactly once, that's asking, does this graph have a walk that uses each edge exactly one time? Right? So is it possible to take this graph and do a walk, so you can start and end wherever you like, but the rule is that you have to traverse each edge exactly once. And what Euler discovered is that, in fact, the answer is no, and there's a parity problem here, and it's not hard to see. Let's imagine a vertex that's not the start and not the finish. So a vertex that's not the first vertex and not the last vertex of our walk. Well, this vertex, I claim that the number of edges incident with it has to be even. And why is that? Well, it's not the first vertex and it's not the last. So at some point, you're going to come in and step on that vertex, and then you'll come in on some edge and you're never allowed to touch that edge again. So you use that edge to get in, and you have to use a different edge to get out. So that first time you walk by this vertex, you'll use some edge to get in and a different edge to get out, but you're never allowed to use those two edges again, right? Maybe you'll visit the vertex again. If you do, well, you won't touch those edges. You're not allowed to. You'll come in on a different edge and leave on a different edge yet. But you can see that each time you come into this vertex and leave, you're going to be using two of the edges incident with that vertex. And since you have to use each of those edges exactly one time, we'd better have even degree. Right? So even degree is possible here, but odd degree, this would be an obstruction. Now, what's happening in this Königsberg graph? Well, you can see that we have 1, 2, 3, 4 vertices of odd degree. So, well, you can't, I mean, there's one vertex that you'll start at and one vertex that you'll stop at, but every other vertex is going to have a parity problem, right? If you take one of those other two vertices, it's going to have an odd number of edges incident with it, and there's just no way to use a walk that's going to use each of those edges exactly once when that guy's in the middle. So this prompted Euler to ask the question: when can you actually do this? When can you find a walk that will have the feature that it traverses each edge exactly one time? Now in this setting, you can see that the first vertex and the last vertex are a little bit different from the rest, right? We have a little bit of a different kind of parity constraint here. And it's nice to actually eliminate that parity condition completely, and we can do so by just insisting that the first vertex and the last vertex are the same, or in other words, insist that the walk be a closed walk. So we can come back and answer the original question of when does a graph have a walk with this starting vertex and this ending vertex that uses each edge exactly one time. But for the reason of working with this, it's going to be convenient to define a somewhat more natural concept where we're insisting on a closed walk. And so let me jump ahead and make that definition. Okay, so our definition here, I don't know why it insists on doing that. So closed walk of a graph G is called Eulerian if it contains every vertex and uses every edge exactly once. A graph is Eulerian if it has an Eulerian walk. Okay, so that's our big definition here. So again, we'll be able to answer other questions here, but the cleanest definition is going to be the most natural here. So we're going to be looking at graphs that have a closed walk. So first vertex equals the last, that uses every edge exactly one time and visits every vertex. So such a graph is going to be called Eulerian. I want to make a note about the nature of an Eulerian walk. If you do have an Eulerian walk, suppose that if I gave you one, so V0, E1, V1 on up to, EK, VK. If I gave you an Eulerian walk, because the first vertex equals the last, you can actually just shift it. So in other words, you could think of this, you could, for instance, think of the second vertex as our new starting vertex and go from there around to VK and then follow E1 back to V2. So I could take the walk that goes, maybe just for emphasis, I'll add one more. So I could take the walk that goes V1 and then E2 and then V2 on to EK and VK. So this looks like right now I've just omitted the first vertex and first edge from the walk that I started with. So it's sort of a new walk that starts at the second vertex and goes to VK. But now I can add the edge E1, and the edge E1 will bring me back to the vertex V1. And so this is going to be a new Eulerian walk. This is still a closed walk. It begins and ends at V1. And this walk is going to have the convenient feature here that V2 is our new starting point. So I'm just informally going to call this shifting the Euler walk. And you can do this anytime you've got a closed walk. So a closed walk, you have a starting point and an ending point. That's part of our definition of a walk. But since the start and the end are the same, you could pick a different starting point further along, follow the walk around, and then keep going until you come to that vertex again. And if I gave you an Eulerian walk to start with, the new walks you would construct by that shifting operation will still be Eulerian. So this is part of the reason that we've used this Eulerian for the special case of closed walks. It's just a nicer property for us. It behaves better. And now what we observed before, so we observed before that if you have a vertex that's not the start or the end, then it had better have even degree if you're hoping to find this this walk using every edge exactly once. Well, now that same logic applies equally well for the first and last vertex, because the first and last vertex are the same, right? So that that first vertex that you start at, you'll use one edge coming out. You might visit it again somewhere in the middle. Each time you do, you'll use two edges, and then you'll use it again at the end. So what's got to be true here is that if you're hoping your graph will have an Euler walk, if you're hoping to have an Eulerian graph, you now have to have all vertices of even degree. And this closed walk this Eulerian walk also has to visit all the vertices, so you'd also better be connected. So our only hope for having a graph that has an Euler walk, an Eulerian graph, would be if every vertex has even degree and you have a connected graph. And in fact, what Euler proved, that's our theorem for today, is that those conditions, which obviously you need, are in fact sufficient. So that's going to be our theorem. Let me write it. So our theorem is that a graph is Eulerian if and only if it is connected and every vertex has even degree. Okay, so the proof. The the only if here, the only if is easy. So if I give you a graph that is Eulerian, then as we've observed, well, it better be connected, because you could just follow that Euler tour to get a walk between any two vertices, and also you'd better have every vertex of even degree. So the only if, I mean, I've written more in the notes, of course, but the only if, I'm just going to mark a check mark. We've discussed this one. You can look at the notes for more detail, but that's all there is to the argument. The if direction is the interesting one here, and this is a very nice and very instructive example of a proof by induction. So now I'm going to have, maybe I'll say a graph G. So now I'm going to have a graph G that is connected and has all vertices of even degree. And I want to show you that it has an Euler walk, a closed walk that uses every edge exactly one time. So for the if direction, that's what we have to prove. And as I said, we're going to proceed by induction. Now, in fact, we're going to proceed by induction on the number of edges of the graph. So we're going to do induction on the number of edges of G. It's perfectly allowed, right? I mean, again, when you're going to do a proof by induction, you can choose what your size parameter is. We can choose anything, really. As long as it's a parameter that's taking on, integer values that bottom out somewhere, we've got a chance. So we can do induction on the number of edges. Perfectly reasonable. If we do this, well, the most obvious base case is when there are no edges. Well, remember, G is connected, right? So for the if direction, I know G is a connected graph and has all vertices of even degree. If I tell you if a connected graph that has no edges, well, then it's not got a lot of options. It's got to have just one vertex. So for the base case, you have just one vertex. So the vertex set of G is just some singleton, say V. And here there is a perfectly good Euler walk consisting of just the vertex V, the trivial walk. Right? Just that single vertex V is a perfectly valid walk. It contains every vertex and it contains every edge. It uses every edge exactly one time. So there you are. So hooray, we've done our base case. So okay, maybe it's not hard, but it's vital to include. Okay, so now we come to the inductive step. And again, I just want to say out loud what we know and what we have. We're proceeding by induction on the number of edges of the graph. So what we know here, we did our base case. That's when the graph had 0 edges. So for the inductive step, the number of edges of our graph G is going to be bigger than 0. And because, based on our assumptions, I know that G is going to be connected and have all vertices of even degree, right? That's what we've got. And now I want to prove to you that G has an Euler walk. Now, how am I going to take advantage of induction? Well, it's not so clear, right? We know, because we're going by induction, that this statement we're trying to prove, a connected graph with all vertices of even degree has an Euler walk. We know that that statement is true for every graph with fewer edges than this one. But okay, how do we use it? It's really not so clear. And what I'm going to show you is some way of achieving that. And it's anyway, I think it's very instructive to see how this goes. It's not like I'm just going to delete a vertex or delete an edge. I mean, indeed, that's almost sure to fail. Like, I mean, well, if I delete a vertex, then if you had another vertex here that was joined by by a single edge to this one, then when I delete this guy's suddenly going to have odd degree. So suddenly you're going to have a graph to which your theorem doesn't give you anything at all, right? Or similarly, if you have a graph where all vertices have even degree and you delete an edge, yeah, you didn't get anywhere. I mean, well, now you have a graph that doesn't have that property. You don't have all vertices of even degree. So although you know the theorem holds true for these smaller graphs, the theorem only tells you something if you have a graph that's connected and has all vertices of even degree. So in order to productively apply our inductive hypothesis here, we're going to need to get back to that kind of a graph. And that's really a little bit of a trick, and it's not so obvious what you should do. So I'm not expecting you to, poof, just see how to proceed here. but I hope you can verify that what we're doing is valid. So again, you're going to see us applying theorems that we know, reducing the graph, applying our theorem inductively in valid settings, and then combining that information that we get to get the thing that we want, to get an Euler walk in the original graph. Okay, so I know that my graph has a non-zero number of edges. Now I also know that my graph is connected, and that means that every vertex has got to be incident with an edge, right? It's possible even there's only one vertex. It could be that you have only one vertex and a bunch of loops, but fine, that's one possibility. That vertex is still incident with an edge. If you have more than one vertex, well, you have to have walks from one vertex to another, and that means every vertex has got to be incident with an edge. Now, every vertex also has to have degree which is even. So I'm arguing that every vertex has to have degree which is bigger than 0, and it has to be an even number. So our observation here is that every vertex has degree at least 2. Right? So every vertex has to have degree at least 2. Now, we proved something in the previous lesson about such graphs. We proved that they have cycles, and we're going to take advantage of that now. So, by a lemma, we may choose a cycle. Ooh. So I can choose a cycle of the graph. And now maybe it's time to draw a picture. So here's our cycle. Now, I'm going to construct a new graph now by deleting the edges of that cycle. So let's let the graph G prime equal G minus the edges of C. Now, G prime is, well, anyway, it's got fewer edges than my original graph G, and that's good news, right? Because that gives us a chance of applying induction, right? We're, in these inductive arguments, you have to get to a smaller case in order to apply induction, and now we do have fewer edges. So this graph G prime does have fewer edges. Now I claim that G prime will also have the feature that every vertex has even degree. And that's pretty easy to see. If you have a vertex of the original graph G that wasn't in that cycle, then when you delete the edges of the cycle, its degree doesn't change at all. If, on the other hand, you have a vertex of the original graph that is in the cycle, well, then when you delete the edges of that cycle, its degree is going to drop by 2. So let's just note all vertices of G prime have even degree. So that's good. Certainly off to a nice start. So G prime is a new graph. It's got fewer edges than our original graph G. It also has the nice feature that every vertex has even degree. But there's no guarantee that it's connected. Right? G prime is not necessarily a connected graph. And well, it's just a harsh reality. That could happen. And that might seem at the start like, okay, well, now we have to abandon hope and give up this line of argument. But that's not really the case. So if G prime is not connected, well, so be it. Then it has connected components. So let's consider them. I'll let, let's say, H1 up to HK be the components of G prime. Right? So H1 up to HK are going to now necessarily be connected graphs. Each of those HIs is going to be a connected graph. And moreover, HI is going to have the property that every vertex has even degree. Right? I mean, it's just, that was true of the whole graph G prime, so it's certainly true of the components, right? So that's great news, because that means each HI is going to be an Eulerian graph. Each of those HIs will have an Euler walk. So I'll just note that HI is Eulerian. Remember that being Eulerian just means you have an Euler walk, this closed walk that uses every vertex and every edge exactly once. Okay, so this is very good news because we get to apply induction. Each HI is a connected graph with all vertices of even degree. It's got fewer edges than our original, so we can apply induction to it. But this doesn't get us the Euler tour of the whole graph. Now we have to put together this information that we've gathered from these HIs, right? So again, we took a cycle that we found in our original graph. We deleted the edges. That might have broken up the graph into a bunch of different components, but each of those components will be all even degree and connected, and therefore it will have a little Euler walk. Somehow now we have to coalesce that information to find the Euler walk in the original graph. And this isn't super tricky. The key feature here is that because our original graph G was connected, every component HI has to contain a vertex of the cycle C. So let me sort of draw a picture. So if you have a component, so what I'm claiming here is if you have a component, this might be H1. Anytime you have a component, it's got to contain at least one vertex of the cycle C. Why is that? Well, suppose I gave you a component over here that didn't contain any vertex of the cycle C. Well, then when you return to the original graph, right? Remember, if I'm at G prime, I can return to the original graph by adding back the edges in C. Well, if this component didn't contain any vertices in C, then when I add those edges back, it's still going to be a component. Then our original graph would have been disconnected. So what it means is that every HI also has to contain a vertex of that cycle C, and I'll give it a name. Actually, let me write it like this. For I equal 1 up to k, HI contains a vertex of our cycle, and I'll choose one such vertex and call it xi. Okay, so in other words, here's my, in my picture here, I've drawn the component H1. So again, when I'm saying component, you have to know what graph I'm talking about. H1 is going to be a component of G prime. So H1 is a component of the graph that we get from G by deleting the edges of that cycle. And this might be the vertex X1. And over here might be the component H2, and that will contain the vertex X2. And maybe over here is, maybe here's H3, and this contains the vertex X3. Right, so they don't have to be, these things can kind of interleave in the manner I've drawn here. However, the HIs are all going to be vertex disjoint, right? You won't have a vertex that's in H1 or H2 because those H1 and H2 are components of some graph, so their vertex sets are necessarily disjoint. So, so H1 will contain some vertex X1 that's on our cycle C, H2 will contain an X2, and X1 and X2 will not be the same onto all of them. And now here's the idea. Well, again, each HI is a connected graph with all vertices of even degree, so it's Eulerian, and by induction, I can choose an Euler walk of that graph. By shifting, I can assume that that Euler walk begins and ends at xi. So let me write that. So by induction, again, so by induction, we may choose an Euler walk, I'll call it Wi, of the graph HI. And by shifting, we may assume that that walk begins and ends at xi. And we may assume Wi begins and ends at xi, right? And now I will tell you how we will construct our Euler walk in the original graph. So I will take, I'll imagine basically starting at a vertex on our cycle and just walking around the cycle, but we're going to take detours. So what we're going to do is we're going to walk around the cycle, but anytime you walk to a vertex that's one of your xi's, as soon as you step on x1, then you pause your travel around the cycle and you just follow that walk w1, that Euler walk for the graph h1, right? So again, let me well, at the risk of muddying my diagram here, let me sort of describe. So we'll start at some vertex on our cycle and I'll walk along. When I come to x1, that x1 vertex is the start and the finish of the walk w1, which is an Euler walk in the graph h1, and I'm going to follow that. So I'm going to come to x1 and I'll do this w1, and that will bring me back to x1, and then I will follow along, and then when I get to x2, I will do this walk w2. Whoa. And then I will follow along. When I get to x3, I will do the walk w3, and then I'll continue on, finishing where I started. And as you can see, that is going to give me a perfectly valid closed walk, and it's going to use each edge of my graph exactly once, right? And then we have lots of different things going on, right? The edges in the cycle are kind of special, right? That initial cycle, we deleted those edges, and that got us to a smaller graph. That smaller graph was not necessarily connected, but each component of it is a connected graph with all vertices of even degree. So each component of that graph is going to have an Euler walk. Each component of that graph, say HI, will also contain some vertex XI in the original cycle. And so we can, anyway, so what we can do is in each of those HI components, we can choose an Euler walk beginning and ending at XI. And now this is how we concatenate them. And this is going to be written better in the notes than I can do it here, but I'll try and say it kind of quickly. Form an Euler walk in G by going around C, but pausing to traverse Wi each time that you step on the vertex Xi. But let's say, but inserting Wi when we touch the vertex Xi. Okay, so I'm sorry, I don't have more space, and this isn't a better medium, but this is written very clearly in the notes. Again, the idea here, we've taken our original cycle, we've erased the edges. That's got us to a graph with fewer edges, so we know that we've got a chance of applying induction because we're going by induction on the number of edges. Now, this graph that we formed does have the feature that every vertex has even degree, which is great, but it's not necessarily connected. So it's got maybe potentially many connected components. But the good news is that each of those connected components is a place where we can productively apply our inductive hypothesis. Each connected component is going to be a graph with fewer edges than G. It is going to be connected, and it's going to have all vertices of even degree, so it will necessarily have an Euler walk. Moreover, we can choose that Euler walk to begin and end at whichever vertex we'd like. Right? Now, what we've done to construct our Euler walk of the original graph is we've observed that, well, when we take our original cycle C and delete those edges, each component in the resulting graph will necessarily contain a vertex in that original cycle. And then what we're going to do is we're going to basically walk around our cycle, but anytime you get to one of those xi vertices, that's the start and end of the Euler walk in the component hi, well, then you follow along that Euler walk and then continue on your way. So that's our proof. I want to emphasize the main ingredients here. Again, you've watched us do a very, very instructive induction proof here. We started with this graph that has all these nice properties. We have made that graph smaller. We've applied our induction. Now, our induction this is not one of these things where you just apply induction and then you say you're done. No, nothing of the sort. You have to take that information that you get. When you apply induction, you're getting some information. And it's best just to view it as such. So we get down to these smaller graphs, we can apply our theorem inductively. That gives us some information. We find these Euler walks, but we have to combine that information. We have to put that together to get the thing that we want in the original graph G. And that's what you've watched us do. So we start with our graph G, we've made it smaller, we've somehow applied the induction. We are then taking that information that we get and combining that to find the desired feature. And that's how proofs by induction work. And that's going to be it for this lesson.